Hello friends, welcome to the Engineering Projects YouTube channel. Today we have started the lecture series of Electronic Devices and Circuit Theory by Robert L. Balested. This is the first lecture of our lecture series and the topic is semiconductor diodes. Before going into the deep knowledge of semiconductor diodes, we have to first discuss about some background topics. We have to discuss about the conductors, we have to discuss about the semiconductors and insulators. What is the difference between the conductors, semiconductors and insulator? Number one difference is the conductors can pass high current. When the voltage is applied across the conductor, then high current can pass through the conductor. For semiconductors, only moderate current, normal current can pass through the semiconductor when potential is applied across the semiconductor. For insulators, no current can pass. As high current can pass, so there will be low resistivity, there will be low hurdle to the electrons, there will be the low hurdle in the way of electrons. Resistivity mean hurdle. So conductors have low resistivity, but semiconductors have moderate resistivity, insulators have high resistivity. Number 3 is example. The example of conductors is copper and aluminium. Similarly, there are some other examples. For semiconductors, we have examples like silicon and germanium, and for insulators, we have examples like wood and mica. Fourth difference is the difference between their band gap structure. For conductors, there is no gap between the valence band and conduction band. This is the valence band and upper band is the conduction band, and you can see here that there is no gap between the valence band and conduction band. But in case of semiconductors, there is a small gap between valence band and conduction band, and its gap is equal to 1 electron volt. So it can be your MCQs. What is the band gap of semiconductors? So band gap of semiconductors is approximately 1 electron volt, 1 to 3 electron volt. For insulators, we have a wide band gap. We have a wide gap and the gap is greater than the 5 electron volt, equal or greater than the 5 electron volt. So you can see here that here is no band gap, so electron can easily move from the valence band to the conduction band. But in case of semiconductors, minor number of electrons can move from valence band to the conduction band. But in case of insulators, no electron can move from valence band to conduction band, so there will be no conductivity, there will be high resistivity. Types of semiconductors. Now we discuss types of semiconductors. There are two types of semiconductors. Number 1 is the intrinsic semiconductor. Number 2 is the extrinsic semiconductor. So now we discuss the intrinsic and extrinsic semiconductor. Here is the difference of intrinsic and extrinsic semiconductor. The intrinsic mean pure and extrinsic mean impure. So all those materials which are pure semiconductors will be called intrinsic semiconductor, and those materials which are impure semiconductors are called extrinsic semiconductors. And students, if you like our videos, if you like our methodology of lectures, then kindly subscribe our channel. So number 2 is the density of electron is equal to the density of holes. Density of electrons is equal to the density of holes. We can say that density of electrons in the conduction band is equal to the density of holes in the valence band. You can see here that this is the conduction band and this is the valence band. This is the valence band and this is the conduction band, and here 5 electrons are missing in the valence band and these 5 electrons are appeared in the conduction band. So the density of electrons in the conduction band is equal to the density of holes in the valence band. So this term, density of electrons in conduction band is equal to density of holes in valence band, but in this case density of electron in conduction band is not equal to the density of holes in valence band. You can see here that this is the n-type semiconductor and this is p-type semiconductor. And in this case, there are the fewer number of electrons which can go into the conduction band, and here are the fewer number of holes which can go into the valence band. So, the density of electrons and holes will not be equal. Number 3 point is electrical conductivity is low. Their electrical conductivity is low, but in this case, their electrical conductivity is high. Their electrical conductivity is low means that equal number of electrons, equal number of holes, but in this case, number of electrons and holes are not equal. They will cancel out the effect of each other, but they will not cancel out the effect of each other. So, conductivity will be high. Dependence, number 4 point is dependence on temperature only. But in this case, as they are impure, they have impurity in them. So, they depend upon temperature. And number 2, amount of impurity. Their dependence is upon 2 points. 2 factors will control their dependence. Number 1 is the temperature. Number 2 is the amount of impurity. Number 5 point is no impurities. In intrinsic semiconductor, these are pure. So, no impurities will be added to the intrinsic semiconductor. But in case of extrinsic semiconductor, we add trivalent or pentavalent impurity. Trivalent means that tri means 3, penta means 5. So, an atom which have 3 valence electrons will be called trivalent impurity, and an atom which will have 5 valence electrons will be called pentavalent impurity. Pentavalent atom, pentavalent impurity. Number 6 point is low operating temperature. The intrinsic semiconductor operate at low temperature, but the extrinsic semiconductors operate at high temperature. Number 7 point is at 0 Kelvin, Fermi level lies between conduction band and valence band. Let us consider the temperature here is 0 Kelvin. So, the Fermi level, this is the Fermi level. This will be in between the conduction band and valence band at 0 Kelvin. But in this case, the conduction band will not be in between. This case, conduction band will not be in between. So, at 0 Kelvin, the extrinsic semiconductors have 2 types. Number 1 is n-type, number 2 is p-type. So, for Fermi level lies closer to conduction band in n-type semiconductor. This is the n-type semiconductor. You can see here that the Fermi level is closer to the conduction band. It is far from the valence band. But in case of p-type semiconductor, the Fermi level is closer to the valence band. It is far from the conduction band. You can see here that and lies near the valence band in p-type semiconductor. In p-type semiconductor, Fermi level lies near the valence band. So, here the examples are silicon and germanium, but in this case, examples are silicon, germanium doped with phosphorus, aluminium, bromine, etc. Here is the current flow process of intrinsic semiconductor. You can see here that these are the silicon atoms. This is the material containing silicon atoms, and here are the electrons and holes. When the potential is applied, this is the positive potential and here is the negative potential, and the electrons are negatively charged. So, when the potential is applied, you know negative and opposite charges attract. Here here is the positive potential, so electron move towards the positive potential and the hole move towards negative potential. And you can see here that when the electron move from here to here, then this will cause a hole here. When electron changes its position, then it will cause hole. So, you can say that the electrons and holes move into the opposite direction. So, electrons and holes move into the opposite direction. opposite hole. This is the hole. So electrons and holes move into the opposite direction. So when the electron move toward left, the hole will move toward right. This is the current flow in intrinsic semiconductor. Same is not for the extrinsic semiconductor because it has two types. So we will discuss it here. This is the silicon. As we can see here, this is silicon, and silicon is the atom which have 14 valence electrons. 14 valence electrons, and you can see here that this silicon have 14 valence electrons. This is the nucleus. In first shell there will be 2 electrons. In second shell there will be 8 electrons. In third shell there will be 4 electrons. So silicon need 4 more electrons to complete its outermost shell. So these 4 silicon will share their electron with central silicon to complete its outermost shell. So this silicon has 4 electrons in its outermost shell, and so let us see here that this is the atom for central silicon, this is the atom, this is the atom, and this is the atom. Let us consider these 4 atoms are for the central silicon, and this silicon want to complete its outermost shell. So it will make covalent bond and it will share electrons. Covalent bond means sharing of electrons. So this silicon will share his electron with this silicon share this electron. So it means that 4 silicon atoms share their 111 electron with central silicon atom and complete its outermost shell. So this is the diagram for the intrinsic semiconductor and for the extrinsic semiconductor. We say that the extrinsic semiconductors are those semiconductors for which impurity is added, and the impurity can be trivalent or pentavalent. So trivalent means that the impurity which have 3 electrons in its outermost shell will be called trivalent impurity, but the impurity which have 5 valence electrons will be called pentavalent impurity. You can see here that when the pentavalent impurity is added to the silicon structure, then N-type material is formed. N-type material is formed when pentavalent impurity is added to the silicon structure. This is the antimony. Antimony have 5 valence electrons. Antimony have 5 valence electrons. So here the 4 valence electrons are of antimony and 4 valence electrons are shared by these silicon atoms. So this antimony have 1 extra electron. 1 extra electron. This electron will move into the structure of silicon, will move here, and this electron will cause more current. This electron will cause more current. So that's why we say here that their electrical conductivity is high. As we know that current is produced by electrons and holes. So the free electron, this free electron will create current, more current. In this case, boron has 3 valence electrons. So in this case, these 3 electrons are shared here, and there will be a vacancy for the electron, and this vacancy, this hole will create current to pass from the structure, and this hole will cause more current to pass from the structure. So I have repeated that the electrons and free holes can cause the current to move from the structure. So in this case current pass due to the electrons, and in this case current pass due to the holes. Now let us discuss the valence band diagram. So, band diagram of intrinsic semiconductor, n-type semiconductor and p-type semiconductor. In this case 5 electrons left the valence band and move into the conduction band, and the Fermi level is in between the conduction band and valence band. But in this case here are the extra electrons. One antimony atom can provide 1 electron, 2 antimony atoms can provide 2 free electrons, 3 antimony atom can provide 3 free electrons, and these free electrons will cause the Fermi level to move to the top, and this Fermi level will move up. And now these electrons have to move from here to here, and then from the Fermi level to here. It means that there will be 2 steps. Electron will move from conduction band to the Fermi level, and then Fermi level to the electron will move valence band to the Fermi level, and then Fermi level to the conduction band. This is the process, and you can see here that it is difficult to move from here to here, but it is easy to move in 2 steps. It is easy to move in 2 steps. It is difficult to move in a single step. So here the electron can easily move from valence band to the conduction band than the intrinsic semiconductor. And in case of p-type material has holes. So these holes will cause the Fermi level to move down, to move bottom, to move into the bottom. So valence band, these holes will cause the Fermi level to move down, and the electrons have to move here. Here is also the 2-step phenomena, and 2-step phenomena are easy. But in case of p-type and n-type material, electrons are majority charge carriers in conduction band. In conduction band, electrons are majority charge carriers. But in case of p-type material, holes are majority charge carriers in valence band, not in conduction band. Holes have to move here into the valence band. Holes come from conduction band and move to the valence band, and we can say that here the electrons are majority charge carrier, and in the valence band the holes are minority charge carriers, and here holes are majority charge carriers in valence band, and in conduction band electrons are minority charge carriers. Here you can see that this is for intrinsic, and in case of intrinsic no impurity is added, these are pure, so this column will be left blank. This column will be left blank, and in this case impurity atom is the donor atom. You can see that antimony here is the impurity atom, and it can give electron. Antimony can give electron, so it is called donor atom. But in case of boron, boron can receive electron. It has hole, it has vacancy. So p-type material, impurity atoms in p-type material are acceptor atoms. Now we summarize, and we will discuss the applications of semiconductors. The application of semiconductors are in electronics. They are used in laptops, mobiles, etc. And they are used in embedded system. They are used in LEDs, light emitting diodes. So these are the applications of semiconductor diodes. Now in the next lecture I have arranged this lecture about the semiconductors. In the next lecture I will discuss about, I will combine these two bands. I will combine the valence band and the conduction, I will combine the n-type and p-type materials, and I will form a diode. In the next lecture, I will discuss about diodes. I will discuss about the PN junction, forward biased and reverse biased PN junction. I hope you will like my lecture. If you like our teaching method, then kindly like, share and subscribe our channel. Thank you.